next speaker is Dr. Michael Schuster from Israel, from Carmel Olefins company. He received his BS degree in chemical technology and also his PhD degree from macromolecular chemistry. And then now he's working in Carmel Olefins. And in our GEOCOND project, he and his team developed phase change materials to be used in grout formulations. Now the floor is yours, Michael. Thank you so much for your participation.
Thank you. So, hello everybody. My name is Michael Schuster, as you have already heard. I am a researcher in research at the Research and Development Department of Carmel Olefins. And the Carmel Olefins is an industrial petrochemical company located in Israel. Our company produces polyolefins, hundreds of thousands of tons of low-density polyethylene and polypropylene annually, some 250 kilotons of polyethylene and some 450 kilotons of polypropylene. Our Research and Development Department is involved in the developing of new polyolefin grades, and the area of our interest and expertise is polymer engineering and science. And today's topic lies quite in this area. So here I will stop my video and will start sharing my screen. Here it is. Okay, so within a GEOCOND project, our company was tasked with developing new novel phase change material to be used as an additive, allowing increase in grout's heat storage capacity.
Michael, can you share your screen?
I'm not sharing?
No. There is a button in the bottom part of the screen.
Just a moment. Sound. Share, just a moment.
There is an icon share screen, yeah. No.
Here, okay.
Yeah, no, yeah.
Okay, okay. Now I'm trying to enter slideshow.
Okay,
yeah?
Thank you.
Okay?
No, great.
Okay, great. So, we were tasked developing novel phase change materials. So, I will introduce phase change material, how it works.
Michael, there is a problem in your voice.
What is my voice?
Now it's better.
Okay, now it's on maximum now.
Okay, it's okay.
Okay. So, so with the focus on organic phase change material, we will talk a little bit about shape stability of these materials, about ways of imparting this important property, and challenges to be overcome on developing this. Then we will discuss the materials engineering concept actually applied in development of shape stable PCM for GEOCOND aspect, for GEOCOND project, and concern in engineering of such materials, and some results. So as you have already heard, GEOCOND assumes that improving performance of shallow geothermal energy systems requires combination of different material solutions for pipes and for groutings. Accordingly, its objectives include development of new groutings with enhanced thermal properties, namely thermal conductivity, which was described nicely by Borchu, and higher heat storage capacity. So if thermal conductivity was achieved via using carbonous additives, heat storage capacity should be achieved via use of phase change materials. Now, reasons for improvement of performance of borehole exchange with improving of their thermal conductivity is quite clear. In order for heat to be effectively exchanged between the heat exchanger and the ground, the heat should easily move out of the heat exchanger and towards heat exchanger. Regarding improving heat storage capacity, it is not so obvious why should it improve the performance of the whole system. Nevertheless, model and experimental studies suggest that in some cases, in some shallow geothermal energy systems, the efficiency can be improved also with enhancement of the ground heat storage capacity via use of PCM. And it is not so obvious. And here we see the excerpts from the study, from theoretical study from 1996, predicted that incorporation of PCM having properly tailored thermal diffusivity into a ground thermal, into the ground coupled heat exchanger should result in significant improvement of its thermal performance. Actually, the study showed also that improperly designed PCM reduces the performance. More recent studies confirmed both these predictions. Some papers implicitly suggest that proper use of PCM in the growth of shallow geothermal boreholes may result in reduction of the required borehole lengths, which is a very desirable result, significantly reducing the cost of installing these systems. So what is PCM? PCM stands for phase change materials, and belonging to this group are materials changing their state from solid to liquid, or changing between two different solid crystallization states over a defined temperature range, phase transition. In order to be useful for thermotechnical applications, this process should be reversible, reproducible phase transition should be, and this process should have significant thermal effect. Changing state from liquid to gas is also phase transition, which can be reversible and have large thermal effect. However, this transition is usually accompanied with a significant change of volume and is more difficult for use in technical applications. In practice, the mostly used phase change materials are actually crystalline materials with high latent heat of phase transitions. There are different families of phase change material, different their chemical nature. They can be organic, inorganic, and tectic. Each family has its advantages and drawbacks, and the relevant for us are organic phase change materials, which are highly crystalline compounds, covering a broad range of melting crystallization temperatures and having latent heat of their transitions close to 200 joule per gram. More specifically, for this project, we used organic PCM. So how does PCM work? PCM stores thermal energy in the form of phase transition. Schematically, if we start heating, supplying thermal energy to a solid crystalline material, its temperature will first rise, reflecting the thermal energy is being stored within the solid as a sensible heat. At some point, we continue supplying heat, we continue heating the material, but the temperature will stop rising. And material will start melting. During this process, the temperature will not rise, but the heat will be continuous to be stored, but now as a latent heat. After completing of the melting, we'll get liquid, so the crystalline solid will turn to amorphous liquid, and the heat needed for this transition will be stored inside the system. If we continue heating, the temperature of the material will resume to going up, reflecting again heat stored inside the system again as a sensible heat, but the sensible heat in the liquid. But the process is reversible, so if now we start cooling the amorphous liquid, its temperature starts going down. At some point, it will start crystallize, and the temperature will stay almost constant. And at this point, the heat will be released as a heat of crystallization. And the material will turn back to crystalline solid, and the process can be reversed more and more times. Ideally, melting and crystallization temperatures should be the same, and when the phase transition starts, the temperature should stay constant. In reality, organic PCM usually show melting temperature a little bit higher than crystallization one because of so-called overcooling, and there are small temperature changes during the observed phase transitions. Early in the process of developing phase change materials for practical use and commercialization, it became clear that in order to be applicable, PCM leakage after solid liquid transition should be prevented. After the material changed state from solid to liquid, it starts flow, and it can leak from the place it should be. And there were search and studies how to impart the property as a shape stability. And the two main practical solutions are incorporation of PCM within a polymer matrix, giving rise for producing so-called composite PCM. So here we see this crystalline PCM within the polymer matrix, or encapsulation, that is enveloping of crystalline of PCM with the solid shell, polymer or inorganic shell. And both solutions allows to material to undergo phase transition of PCM inside the shell or matrix to go from solid to liquid, but the whole system keeps its geometry and dimensions, which is called shape stability. And in some reviews, it was actually signed and mentioned that availability of commercial PCM composite materials and encapsulated PCM is crucial to development and commercialization of PCM applications. It should be said here that imparting shape stability via immobilization within either matrix or within the shell comes at the expense of PCM thermal effectiveness. However, it is highly desirable to get the shape stability to be convenient in the technical uses. And here comes Carmel Olefins. Having experience and expertise in polymer engineering, Carmel Olefins has developed a novel concept allowing cost-effective, recyclable, shape-stable phase change materials in granulated or shaped form to be manufactured using conventional plastic compounding equipment. The challenge was finding a way to achieve the desired balance of properties while increasing PCM content to above 70%. The concept was first validated in domestic hot water applications. However, it allows designing materials suitable for various thermal energy storage applications. Specifically for shallow geothermal energy applications, the concept required modification of the material composition, manufacturing equipment, and the procedure. The forms in which shape-stable PCM of Carmel Olefins can be produced include filament form, granulated form, or compression molded plaques. Shape instability of PCM can be illustrated by a simple comparative experiment. If we'll take a classic organic PCM, pelletized paraffin wax with melting point temperature about 60 degrees, and we put granules in the hot water at the temperature of about 80 degrees, the pellets having density lower than the density of water will float on the surface, gradually melting. At some point, finally, a layer of molten powder will form on the surface of the water. Viscosity of this molten paraffin is quite low, similar to that of viscosity of vegetable oils. And using such material in technical applications is quite problematic because of its tendency to leak out. On the other hand, if we'll take a pelletized or shape-stable PCM containing about 80% of the same paraffin wax, and we'll put it into the boiling water. Here the water is boiling. We will see that the pellets stay pellets, the plaque will stay plaque, both keeping their geometry and size, despite the paraffin undergoing phase changing material and changing in state from solid to liquid. The cost of imparting the shape stability is about 20% reduction in the thermal energy storage capacity. Latent heat of this material is lower than latent heat of pure wax. Concepts of engineering shape-stable PCM our shape-stable materials are multi-component materials, and considerations of Carmel in their engineering are application-specific and include selection of the components and optimization of the composition. The thermal energy storing component should have required transition temperature and latent heat. The matrix should be selected or engineered to provide processability, shape and thermal and chemical stability, and it should retain maximum PCM maximum as much as possible. We use additives facilitating processability of the material and providing required additional properties such as mechanical strength, density, thermal conductivity, and so on. All the components should be compatible with each other and should properly interact to form in situ required morphology and structure. And the final composition should provide the required balance of thermal properties, processability, shape stability, and mechanical strength. So these were aspects of concern during engineering of the PCM. Now, our materials produced using conventional polymer compounding equipment. The equipment should allow convenient and stable feeding of all the various components, their proper dispersion and homogenization, effective cooling and pelletization of the final composition. So barrel and screw of compounder should be properly configured, and the auxiliary devices like feeders, chillers, pelletizers should be properly adapted. The process considerations of concern in developing PCM production process include physical form of the components to feed, feeding order, compounding conditions, pelletization type and conditions. And finally, the process should allow facile, easy manufacturing of shape-stable PCM with good mechanical properties at maximum possible loading of thermal energy storing component. For production of our PCM, we use conventional laboratory twin screw compounder. Before I start the clip, it is quite noisy, so it will be maybe difficult to explain what you can see. But here we see the final part of compounder. We see die with single hole. We see molten polymer composition exiting the hole, entering the cooling bath, going through the cooling bath, solidifying, and finally entering the pelletization facility. So now I will start the clip, hoping that it will. Yeah. Okay, so this way we can produce up to 4 or 5 kilograms of pelletized material per hour. We can stop on producing filament without pelletizing. Our partners from Sweden spent quite significant efforts and energy developing composition of grout, which can incorporate our material. And the results of this effort you can see here on comparison of phase change material before introducing into the grout and after. And what we can see that the shape and size of granules of the PCM are kept. We see the granules uniformly distributed more or less throughout the grout and interacting. We see no clusters. On the cut surface of the same grout, we can see some more indications of good work done by our partners. We see the particles incorporated into the grout. We see not much detachment of the organic particle from inorganic matrix, implying good interaction. You should understand that these particles within this grout and survived contact with quite aggressive components of the cementitious grout, very alkaline media or medium, and they stay inside the matrix even after cutting it and transporting it. So implying that there is a good thermal contact of PCM with the grout. This way, the PCM demonstrated its chemical resistance, shape stability, and sufficient mechanical strength. And indeed, preliminary tests performed by RISES in Sweden showed thermal activity of the PCM within growths, and the experiments are still ongoing. And here we came to a close of the presentation, and thank you very much for your attention. That's it.
Thank you so much, Michael, for your nice and informative presentation.